Hello. Hi, everyone.
Good morning, ma'am.
Yeah, good morning. Hi, Jacob and Akash, Sahana.
Hello.
Yeah,
Hi, hello.
morning all.
Yeah, hi.
So today we are going to start a protocol session. So today we are going to discuss on introduction to all different kinds of protocols in VLSI, overall system on chip design. And you already know the schedule, right? So how we are going to discuss 5 different protocols according to our schedule, weekends, Saturday and Sunday. Today we will discuss overall, you will get overall idea on system on chip VLSI protocols. Okay. So coming to the introduction, can you tell me what is mean by protocol? What is the use of protocol in VLSI, not only in VLSI, embedded system applications or network applications, whatever.
It's the medium of communication between two devices.
Okay. And what are the rules, the basic rules we need to follow? Any answers? Others?
It should be capable of exchanging data.
Okay. Fine.
And must follow some rules, must have some controls.
Okay.
Data, some data
Hmm.
input, data output limit.
The limit with input
Size,
data and output.
yeah,
Okay.
and speed limit, number of cycles.
Okay. The speed, frequency, all these things will be dependent on its functionality, right? How it will be dependent on protocols.
Okay, protocols are like number of inputs and number of outputs it is connected, like single to one to one or one to many. Like
Okay, fine. Okay. So coming to the classification of system on chip protocols, we have different types of protocols in overall SoC. Okay, first of all, can you tell me what is meant by SoC, system on chip architecture in VLSI? System on chip architecture in VLSI.
It's a collection of different subsystems used for different functionalities.
Okay.
So all the components of the computer are present on the same chip. Like this, all the subsystems are connected together.
Okay. Any other answers? Fine. So if you observe here, it's a system on chip design. System on chip design in the sense it contains all functional blocks. Whatever we are using different types of architectures in a mobile phone or laptop. The PCB board, if you observe the olden computers, we have the motherboards. Motherboard in the sense where we have a PCB board and we will put all the components on a single board. Nowadays everything is system on chip design. On a single chip, we are going to integrate all different functional building blocks. That's what we call as a system on chip design. Okay, so here it contains one related to the processor subsystems and memory related subsystems. Also, it contains different functional blocks like Wi-Fi, GSM module, or Bluetooth, or graphic processors, or even low speed communication devices like any IO peripherals like keyboard, mouse, which are connected externally. So entire system on chip architecture contains these type of different functional blocks in the sense memory controllers or different types of memories, whatever. Okay, so whenever is this visible properly, clear? Not clear, huh?
No, ma'am, not clear.
Okay. No? Is it clear now?
Yes, ma'am.
Okay, so if you see here, this whole architecture we call it as a system on chip. Okay, so in system on chip there will be multiple number of subsystems. Subsystem in the sense, if you see here, it's related to the CPU subsystem, this entire block, and here it is related to the video subsystem and image related subsystems where image processing, the graphics, 2D graphics, camera related things, everything done in this type image subsystem. Next, a radar subsystem, like that machine learning subsystem, the techniques where we put image processing techniques and the deep learning techniques, all these things applied here. And memory related subsystems like DDR memory, SRAM, or ROM memories, or PI interconnects. We'll use different kinds of memories, right? All memory related things comes under memory subsystem. And here high-speed wide peripherals, wide peripherals in the sense of PI or USB or Ethernet or PCIe, everything comes under this subsystem. And wireless subsystem, Wi-Fi module, GSM or Bluetooth module, or 4G, 5G, whatever the communication blocks are there, everything comes under wireless subsystem. And functional safety, regarding a security or fuse functional blocks or parity checking functional blocks, everything comes under functional safety subsystem. And different types of IO peripherals which are connected internally or externally, like a JTAG or a display, mouse, keypad, all these things comes under some one type of subsystem. Okay, so internally, whatever these building blocks we are calling as a subsystems, right? But internally there are small blocks, A76, A76, these four quad core, four number of cores are there, right? Basically, in a CPU subsystem, what will be there? Different types of processors like a graphic processor unit or digital signal processor. So, and it contains some cores or cache memories. So everything combinedly we put in a CPU subsystem. These small building blocks we call as a IPs. Okay, each IP have its own functionality. Cluster of IPs we call it as a subsystem. Cluster of subsystems called as a system on chip design. Okay, so if you observe here, Wi-Fi is one type of IP. GSM is a IP. 3G, 4G, LTE, that is also one functional block. It's called a IP. Like that Bluetooth, if you put here, it is one IP. Okay, so this cluster of IPs we will call as a one subsystem. And here, if you observe memories, we have different types of memories as RAM, DDR RAM, and HBM, LPDDR. These are the versions, DDR1, DDR double data rate memories. Currently, in most of the industries, we are using DDR memories. Okay, so it's a high speed memory. And PI interconnects we use here. So these all are individual IPs. All IPs we are combining in a one subsystem. Okay, so These are the different types of subsystems based on each because memory related is different, Wi-Fi wireless related different, high speed wire peripherals different, IO peripherals different, CPUs different, video related different, image related different, right? We are making it as a separate blocks we call as a subsystem, and all we are connecting at a one module, one architecture. That's what we call as a system on chip design. Okay, everyone got clarity what is mean by IP, what is mean by system on chip, what is mean by subsystem? Any doubts here? No doubts?
I have a question. So inside the subsystems, we have interconnects, right? So, like there are different SoC like for servers, etc. There we don't see like heavy maybe subsystems like image and vision. We might just see like peripherals and maybe processors. So, how do we differentiate that kind of SoCs with these kind of SoCs where there are many subsystems?
You're you're talking about where we connect with the servers, right?
Yeah, like servers, subsystems, sorry, servers SoCs might look different,
Okay.
and like mobile full chip will look different.
Mhm.
So, like even the bus protocols there will differ, right? So, what I'm trying to understand is, like inside each subsystem, we will still have interconnects, and all those interconnects are connected externally
Mhm.
through another mesh, right?
Yes, actually, this SoC is a basic common system on chip design. But if you go to mobile SoC, obviously every SoCs are different. A mobile SoC is different, and coming to laptop system SoCs, both are everything is different. But whatever we are saying here, it's just a basic idea. But internally, if you go exactly what the industry is going to put the exact SOC means it have lot of external blocks, like it contains debug units, it contains DBGSC blocks, DFT blocks, video related, and even a scalable fabric, the data fabric control hubs will be there. So everything that is totally different. Whenever we go to industry, then only we can understand every block to block, because every company have its own SOC architecture. Okay, so these all are common as system on chip designs where every SOC have, but without these, there are a lot of blocks involved in the actual SOC. Okay, coming to the server, suppose if you are telling we need to connect with the server to the main SOC, obviously we will connect with the ports to the one system on chip design to the another system on chip design. Like that, multiple SOCs will be connected together also for complex applications.
Okay, that time server will not become like a subsystem. It'll be a separate SoC and another SoC is getting connected.
Then
Um,
internal server, if you connect to internal server functionality, hardware will be there. But if you are connecting with the external, suppose that this hardware, this SOC is related to some your computer. Okay, your computer is going to connect with another server where we put everything in a one type of application related, or everything we store in the server's box, right? So I thought you are talking about that. Then we will
mm,
connect externally this laptop to another server through wire or wireless. We can connect both. The processor will get understand, like this processor will be communicated to server processor.
okay, okay.
But
So that
inside
means two
also,
SoCs are talking. Okay.
SOCs to SOCs we can connect, but inside these also we will have the simple network communication in the sense what you call as a server. Network devices will be there internal. These also like a security purpose or fuse related purpose. Everything will be there in a system on chip design. If you talk
Okay.
with normal applications.
Okay.
Okay.
Yeah,
Any
that
other doubt?
answers my question.
Okay. Everyone understood what is the difference between IP, SOC, and subsystem? Any doubts? Okay. Okay. So if you see here, while we are connecting one computer, one subsystem to another subsystem, or one IP to another IP, these blue color, if you observe these, we call as a interconnects. So in every subsystem here, there is a green color interconnect, and here blue color interconnect, and here also blue color, and here orange color, here blue color. These all are interconnects. That mean suppose here there is a processor, and if you see here green color, and also the name, if you observe coherent in interconnect and non-coherent interconnect. What is the difference between coherent and non-coherent? In the sense, all processor related, wherever we run the instructions, all processor related will comes under coherent interconnect. It has cores. Okay, wherever we have the core, all these things comes under coherent. Wherever we don't have cores, only hardware, only just a digital hardware, those comes under non-coherent interconnect. Okay, so that's why here green color interconnects are there, here and here. Okay, and next, you already know CPU means it's a central processing unit. It communicate with every small device of the system. Okay, so however our human brain is communicating with every signal in entire body, it just give the instructions, whatever we are doing some work or we are talking something, that instructions will be given from the brain, and also whatever the output we are doing, that also going to the brain. Based on that, our system will work, right? Same here also, the processor will give multiple instructions to entire system. Suppose here you are connecting your Wi-Fi. Suppose here from Wi-Fi we are connecting to our any of the system. So whatever the task we are going to do, whenever we click here, the processor give the instruction to open these particular icons. Okay, so whenever we are clicking here, it just open and we do entire task. That is what we do. But internal, how it is communicating, in the sense, to the software, always the hardware will be communicated, right? Hardware and software both are mutually communicated. Okay, so all those things happen through the instructions. Okay, the processor will provide the instructions, whatever the number of cores we have connected. Four cores, four cores, in the sense it do four number of tasks parallelly. You already know one core will do two number of tasks. Suppose two cores means four tasks. If there are multiple number of cores, more number of cores, in the sense, we can, the application will be speed up. Okay, we can run multiple number of applications at a time. The processing speed will be more, right? That is the use of more number of cores. Okay, same way here, whenever doing some task, and here the entire hardware, even a single signal also, internal communication signal also connected to the processor. Okay, so while the processor is communicating, suppose the processor here, CPU, maybe communicate with GPU. Not only GPU, it may communicate with this image processor, and the same GPU will communicate this Wi-Fi module and GSM module, and same processor will communicate here with a display or JTAG. Okay, it communicate with everyone. So whenever it is passing the data, communicating means what? Nothing but transferring the data, right? Read data, write data, handshake operation will be done, right? So whenever it is transmitting the data or receiving the data, it should follow some rules. Why? Because maybe here the memory will work at a high speed. The processor also work at a high speed, at high frequencies. But this display is a very small peripheral or interconnect or any functional block. It's a small bandwidth functional block. Okay. So to communicate with high speed to low speed, we need to follow certain rules. Okay. Same in memory also communicating with the memory also works at a high speed. Okay, so to communicate from memory to low speed, we need to follow some certain rules. Another thing, processor always communicate through parallel data. Okay, it always send the parallel data. But some of the peripherals here or some of the functional blocks may not take the parallel data. They are not intent to the parallel communication. They always work with a serial. Okay, suppose in your laptop, whenever you are connecting your mobile phone, suppose this is my mobile phone and connecting to the laptop, how we are connecting through the USB cable. There will be a USB cable or there will be a C port pin, whatever. We are communicating our mobile phone to the laptop. So this communication channel, is it doing parallel communication? No, right? Serial communication. Mostly all interconnects will be serial communication here, the channels. But here parallel is processor is communicating parallelly, but here how it will transfer serially, that's what the rules we need to follow. Okay, certain rules we need to follow. And also some signals will be bidirectional and some will be unidirectional. Okay, that also is a rule, one type of rule. Okay, so to follow all these rules, we have different types of protocols. Protocols are nothing but set of rules. Okay. For parallel communication, we have some type of protocols. For serial communication, we have some types of protocols. At high speed side, we have some protocols. Low speed side, some protocols. So all protocols are divided into the different classification based on the rules. Okay. So today we are going to understand what are the different types of protocols and where we use all the protocols in a system on chip design. Everyone got clarity now? What is mean by a protocol?
Actually, in the subsystem, if any IPs are communicated, want to communicate with each other, then how they will do?
IP to IP. Yeah?
Yeah.
IP to IP also there will be a these bus connections will be there.
Okay.
Interconnects. IP to
It is
IP. Internal IP also there will be we have inter-communication protocol, intra-communication protocol. Based on that, inside the IP also we have the communication interconnects.
okay. And let's consider like as
Suppose
like
see here, Wi-Fi is a IP, GSM is IP, and this LTE is one kind of IP, and the total 4 IPs are there in this particular subsystem. So how this IP Wi-Fi to GSM are communicating? This is also one interconnect, blue color one. So through this blue color one, all this will be communicated, and parallelly all this data will be sent to this big interconnect, and through this the data will be coming to the processor, like that. And bidirectional, same.
okay. And one more thing, like for the external things, like let's consider mouse we have, and we are communicating with inside, right? So inside the mouse there will be no IP, right? All the IPs are present in SOCs, which is in PC. So
Okay.
so what will be in the mouse? Like I mean, any
Mouse
IPs will.
itself, it is a IP. Itself, it's a functional block. Mouse itself, it have only one functionality, just to click right and left or drag operation. Itself, it have a functionality, and that thing we are communicating from outside to interconnect with the SOC or laptop.
Okay, so the USB stands here like inside the SOC, right? So from the SOC socket, there will be some bus which will be go there. Is it?
Yes, you will get clarity. We'll discuss more on that.
Yeah, sure. Yeah, fine.
Okay, everyone got clarity what is meant by a protocol. So in system on chip design, to transfer the data one subsystem to another subsystem, we need to follow certain rules in terms of parallel communication or in terms of serial communication or high speed, low speed or bidirectional or single directional or half duplex or simplex or full duplex. There are different types of rules we need to follow. So altogether we have divided into the number of protocols, because each protocol have its own specification, right? Every protocol doesn't have the common specification. Some protocols will work at a different, having more number of features which are more advanced protocols, and then some protocols have less features which are like old versions. Okay, so that's why we have divided into the various kinds. So we'll discuss all the protocols now. Okay, so coming to the classification of VLSI system on chip protocols, we have different types. One is a on chip communication protocols. Okay, on chip communication, memory interface protocols, high speed serial protocols, and peripheral interface protocols, wireless communication protocols, and debug and test protocols. I think you heard first time for about all these protocols. Commonly we heard about very few protocols like UART, I2C, ABB, AHB, AXI. If you go beyond that, USB, PCIe, or Ethernet, or SATA, or CAN, or JTAG. These are the common protocols. But if we go beyond the overall VLSI in terms of wireless, in terms of debugging, in terms of memory, in terms of on chip or peripheral, whatever. Okay. So first of all, if you see here, on chip communication protocols, nothing but these protocols handle the data transfer between blocks within an SOC. Suppose here SOC is there, blue color interconnects. All these blue color interconnects comes under on chip protocol, on chip communication protocol. Maybe it's a bus based or network related. We have both. Bus based will be there, network NOC also will be there, right? Every processor, every system on chip, we have the NOC also, network on chip, network related protocols also. Okay, so on chip communication protocols are nothing but the data transfer between the different blocks within a SOC. And next, memory interface protocols are nothing but communication between processor to memory. So if you see here, uh, top one is a processor related CPU subsystem, down one is a memory related. For majorly processor to memory communication, how it is happen means through, if you see here, DDR, DDR4, LPDDR, DDR5. So double data rate, LPDDR in the sense a low power DDR. Like that we have HBM, high bandwidth memory, GDDR, graphics DDR, and ONFI will be there. Here, these not mentioned. Open NAND flash interface will be there, like that joint electron device will be there. So there are different types of memory protocols are used only for communication between the processor to the memory. Okay, that's what we call as memory interface protocols. And next, coming to the high speed serial communication protocols. High speed serial communication in the sense, mostly high-speed data transfer occurs SOCs or external interfaces. Just a second. Okay, so high-speed serial communication protocols are nothing but it transfers the data across the system on chip and also external peripherals. Okay, so what are the external peripherals? USB. USB is a current trending. Not only current trending, from past 10 years we use a USB protocol. Okay, so USB, just now you told, right? How we communicate from in this one device to external device. So USB will be used there. And also PCIe. PCIe is internal system on chip only. to communicate high speed to high speed. Mostly it's also serial communication. Like that we have SATA, serial ATA, and non-volatile memory express will be there. Thunderbolt will be there. These are various type of, based on the industries they use particularly. Suppose even in on-chip also, we know only AMBA protocols, but if you go beyond that, like in industry, there will be lot like Wishbone or Core Connect by IBM, Avalon by Intel. There will be different types of protocols will be there. Okay, so next, coming to the peripheral interface protocols. Peripheral interface in the sense, these also used to interface with the peripherals and external devices, both inside the system on chip and also outside the system on chip. Majorly, we have I2C, SPI, UART, CAN, controller area network. Coming to the network side, we have the CAN or local interconnect network. These are different types. Okay, mostly we use within SOC or intra and inter communication. We will discuss both clearly. And coming to the wireless communication protocols, wireless means what? Mostly we use a Bluetooth, Wi-Fi, Zigbee, like that. Okay, and debug and test, these are the most important for like a 5+ year experience engineer or 10+ year experience engineers will work mostly on debug and test protocols. That means one of the most important is JTAG. Most commonly we use the JTAG, joint test action group. I will discuss this also clearly. And serial wire debug will be there, like embedded core test will be there. IJTAG, like internal JTAG will be there. So these are various classification of protocols. We will discuss one by one clearly. Any doubts still here? Any doubts? Yeah, am I audible?
Yes, ma'am, no doubt.
Okay. So coming to the clear understanding, we'll try to understand each protocol. Okay. So coming to the on-chip communication protocol, as I told that these protocols handle data transfer between different blocks within an SOC. Okay. Majorly in this training, we are going to discuss this first one, AMBA, Advanced Microcontroller Bus Architecture, AMBA protocols. Okay. In this, we have three types of AMBA protocols: APB, AHB, AXI. Okay, so APB, AHB, AXI are bus interconnects. So whatever the blue color we are seeing here, all these are AMBA protocols only. Okay, in these three, APB, AHB, AXI, AXI is one of the major, like very high speed peripheral interconnect. Okay, so it have lot of features also. There are, it is very advanced. Even in nowadays, most of the industries use AXI, and one of the advanced protocol is PCIe. Okay, so this blue color, where it is connected, like from which block to which block, from all subsystems are connected to the blue color interconnect. Okay, so even processor side and here IO peripheral side, everything is communicated. But if you observe another thing, the processor is connected directly to the AXI. Suppose it's a AXI. Okay, high speed side we use AXI, low speed side we use APB. Okay, so processor side if we use AXI, but low speed side AXI will not work because it works at a very high speed. Low speed means the frequency mismatches will be there. The data will not communicate properly, right? So for that purpose, low speed side we use APB, and we will try how we can transfer high speed data to low speed data. That's what we need to learn majorly. Okay. So how the bridge is connected from high speed to low speed, how the AXI and APB are connected, we need to understand. Okay, so we are going to learn in detail about the AMBA protocols. And coming to these Wishbone and Core Connect and Avalon, these all are open source. Just Wishbone and Core Connect are open source, but Core Connect also not a open source. Avalon also not a open source. Only in industry we need to learn those things. If you work with the IBM or Intel, we need to learn there. But Wishbone is a open source, but not we never use like AMBA protocols. Okay, these also used to design the FPGA and ASIC designs, and we have both pipeline and non-pipeline, but not like a AMBA. Okay, and coming to the network on chip protocols. In network on chip protocols, there are mesh based. So, what is meant by mesh based? It is just connections, how the mesh is connected, or torus or hybrid NOC architecture. This is just architecture wise how we are converting the network. The cross trigger network will be there, right? So based on that, these different types of protocols are divided. And next, memory interface protocols. DDR, DDR1, DDR2, DDR3, 4, 5. Before I have shown, right, how the processor to memory we are connecting. Through these protocol only we need to connect. Why? Because memory register, whatever the register we are storing the data properly, the address and data, everything will be debugged by using these protocols properly. So normal protocols we cannot debug the actual data, memory related data. That's why specifically for memory we use these type of protocols, HBM or GDDR, graphics DDR. And sixth to seventh is very rare, we use very rare. But if you are applying for the industries and all, this is one of the best DDR you can learn. SDRAM or LPDDR is also fine, low power DDR. And next, high speed serial communication protocols, majorly used to transfer the data in SOC and to the external devices. Okay, so PCIe, what is meant by PCIe? Mostly we use in all system on chip designs, we have a PCIe, right? It's a very high speed serial communication protocol. It's not a parallel, it's high speed serial communication, and we connect in terms of lanes. Lanes in the sense multiple number of lanes we will connect at a time. Multiple data transfer can be done by using the lanes. Suppose um, like configurations we have x4, x8, x16, 16 data. It's not parallel communication, serial only, but 16-bit data we will communicate through the lanes. If you see the normal I2C protocol, how we communicate the 16-bit data? In serial communication, the 16-bit data can be transferred 0th bit, 1st bit, 2nd bit, 3rd bit, 4th bit, 5th bit. We don't have any lanes, single line, one by one bit we need to connect. But if you go to PCIe, we connect a number of lanes. That means all this 16-bit data will transfer serially, but in a single lane. Okay. So you understand now how the speed will be increased by using PCIe, right? And also it eliminate the shared bus. We don't have the shared bus. It will communicate from point to point only using multiple lane configurations. Okay, like that. Currently we are using USB protocol, but USB we are not learning here. We are going to learn UART. UART is also same, where we connect external device to the internal device, but UART is a very olden version. Okay, but USB is a present. We have versions in USB. We present in most of the applications we are using USB 4.0 is one present version, right? So USB is also a serial peripheral protocol. And next is SATA. SATA is mostly for serial link to transfer the data between CPU and the storage devices. Okay, we have the storage devices, like what are the storage devices we have? HD or SSD. We have the storage devices, right? To communicate with that, we use a SATA. And also for SSD, mostly we use non-volatile memory express. It's a serial communication. And Thunderbolt, CXL, these all not we doesn't use, but very rare. Okay, so these are the classification of high-speed communication protocols. Low-speed serial communication protocols are I2C, SPI, UART, CAN, LIN. In this, we are going to learn I2C and UART. UART is a asynchronous, I2C is a synchronous. Once asynchronous, one synchronous, we are going to learn peripheral interface. That means both we will connect external device and also internal device. Okay. So, and the CAN, LIN are coming to the network related. For network purpose, we use these two. And coming to the wireless communication protocols, one is a Bluetooth, Wi-Fi, Zigbee, NFC, LoRa, mostly used protocols. And one of the major, before I told, right, for debugging purpose, we use a JTAG. So what is the majorly where we use in the sense? For debugging purpose, in verification field, debugging is also one of the major role in pre-silicon and also in post-silicon. In pre-silicon, we do normal verification directly using the test case. But in post-silicon, that means after chip is ready. Suppose it's a hardware chip, the chip is ready. If you want to verify this particular chip, what we need to do? First of all, we need to connect to the computer. Then we need to check what are the different uh, errors in the chip. So inside this chip, how we will get to understand where we have the errors, in which block we have the errors, because it have the processor, it have cores related, and it have the memory subsystem and IO peripheral subsystem, and lot of interconnects will be there. South bridge IO, north bridge IO, data fabric, control fabric, everything. There will be lot of things involved in the system on chip, right? But we don't know from where it is getting the error. Okay, so that's why every block we will connect with some debug units. Every block we will connect with the debug unit. So here in the debug unit, we will get to understand what are the errors, what are the tests are not passing, what are the failed tests, passed test, everything we will understand here. Maybe you may get the doubt, why do we get the errors in a chip after manufacturing? In after manufacturing also, we will get the debug issues. Okay, after, that's what we call as a pre-silicon and post-silicon verification. In post-silicon also we do the verification. Okay, so whenever we are connecting all these things to one debug unit using the cross trigger network, this this is separate hardware which we add to the main system on chip design. It's a separate hardware. Okay, so this debug on chip debug will be connected to this host debugger, where in computer we have the certain number of tools. Through the tools we access the data of this everything. Okay, so how we are connecting here? Through the JTAG. Through the JTAG we connect. JTAG is a separate protocol. Okay, if you are interested after these protocols, you can learn about JTAG. But we only JTAG, if you learn, there is no use. You need to learn at least a post silicon verification. how the debug unit connecting here and how the debugging process happened, how to debug the test cases for C test for core test cases, how the C are debugged. So if you learn these things, better you can put as a project, as a client level project. Okay. So this is what the JTAG protocol for debug and the test protocols. We have JTAG, serial wire debug, IEEE, embedded code test, and JTAG. Okay. So everyone got clarity? What are the different types of protocols we have?
Yeah, here, like you are mentioning peripherals and external devices. So both are same, or what is the difference?
Internal peripheral devices will be there and external peripheral devices will be there. Suppose if you see here, I2C and SPI are connected internal device to device. UART is connected to external device, like that. See,
Okay.
use it for interfacing with the peripherals and external devices. Peripherals internally with and external devices also we connect, but both are different. Here we will understand what is intra and inter, then you will get the point.
Okay. And regarding the JTAG and SWD, this will be done by the firmware engineers, right? In the industry.
Not firmware, not only firmware, normal verification engineers also will use JTAG in post silicon only.
Okay. So currently, I'm working on that only. I got task. So
Okay.
it's a pre-silicon also, as you mentioned, right?
Okay.
So means the chip is not ready, but we are verifying through the JTAG.
Yes.
So like how it will be like? It's like as you say, it's IP and
JTAG is just like a communicator. Suppose here in a computer to mobile phone, before we have connected, right, system on chip to the mobile phone, how we are communicating using the USB port. This channel is a wire connection. How the data is transmitting through the wire to the USB. Serial data transfer will be done from this processor to this processor, right? In the same way, a JTAG have its own functionality where it can access this debugger data. JTAG is nothing but it's a wire, just like a wire connection. That through that wire, we will send the data to the computer. I mean software. Suppose AMD use VSIM software, VART tools. Through that tools, we check the data.
okay, yeah. That JTAG I have seen, but this adapter I didn't see in any. So it will.
Here we call it as a adapter or even wombat. Wombat, these are nothing but like FPGA, which communicate with this hardware. We connect the extra FPGA. Wombat will be connected. Through
Okay,
that
so
wombat, we will send this JTAG data to the computer.
okay, yeah, got it. Thank you.
This is our main chip. To the main chip, we will connect one FPGA, small FPGA. We call it as a wombat. This wombat to this computer will have the communication. That communication through JTAG. Here JTAG adapter is nothing but I don't know whether here they given I think as a FPGA only, but normally in industry we call it as a wombat FPGA. Through that we connect with the computer.
Okay, yeah, thanks.
I will share you the pictures later. I will share you main SOC picture in how exactly we use and also this wombat picture.
Okay, okay.
Prasanthi, this JTAG is used in DFT process, right?
DFT majorly we use because in DFT also we will connect. DFT also similar where we connect the hardware kit and by using the scan chains mostly we check we just test the every gate to gate right So there in mostly DFT we use JTAG, and DFD also we use JTAG. DFT means designed for debug. It's a post silicon verification. So coming to the sub classification of SOC, yeah, any doubts?
Yeah, sorry, I have a doubt. So in pre-silicon, after doing all the verification also, while manufacturing, so after the chip is ready, why we might get errors, ma'am? Like what might be the causes for the error?
After it is not after chip is ready. After chip is ready, that means now before getting into the market, after dumping the data into the hardware, into the silicon, we don't know whether we get the errors or not, right? Even post silicon also we will get the errors, because suppose in RTL, if you see, will you tell that without any errors we can go directly for verification? Is it possible? We don't know, right, whether RTL is correct or wrong. Directly we cannot send RTL software netlist to the physical design until unless we do the verification. Same after dumping that software into the hardware, we don't know exactly we will get everything is correct. Okay, because of internal clock issues will be there, or internal minimum node connection issues will be there. So we'll get the errors automatically, and that too in the pre-silicon verification we can't tell 100%, even 100% coverage we get. At any point of time we may get the errors whenever we dump into the hardware. That's why post-silicon verification also must. Once post-silicon verification also completed, once we get 100% coverage from DFD team, then the chip is ready. We can process in a bulk number of, and it is out in the market like that. Okay.
Okay, ma'am. Got it.
And based on the devices, till now we have discussed all different types of protocols. I think all we have covered, right, from on chip AMBA to network protocols and memory related protocols and high speed related. In these we are going to discuss two from peripheral interface and three from bus protocols. Okay, and wireless JTAG, all protocols we have discussed. So within these, which one will work like a serial and parallel and a full duplex or a half duplex, or which are connected within the device and outside the device, we need to understand. Okay, so based on devices communication, first one is inter-system communication and intra-system communication. Inter-system communication means between two devices. Okay, whereas intra-system communication means communicate within one device, within a device. One device means within a device, two blocks will be communicated. Outside the devices means two devices or communicate. Suppose you are computer to mobile phone, computer to scanner, computer to printer, computer to mouse, computer to pen drive. Like that, we have lot of devices outside where we communicate. All those things are communicated using USB, UART, USART protocol. Okay, nowadays mostly we use USB, but olden version is UART, Universal Asynchronous Receiver Transmitter. Okay, so next, intra-system protocols are I2C, SPI, CAN. I2C, SPI or communicate with the normal functional blocks. CAN in the sense network related protocol. So if you are working with the network data, network system on chip, network on chip, then CAN protocol we need to use. Okay, so these are the classification. Understood, everyone? You may get the doubt, then what about the AMBA protocols, whether those are inside or external device communication? You may get the doubt. AMBA protocols are bus connections, parallel bus connections. We communicate within the functional blocks. Okay, clear till here?
Yes, ma'am.
Next, subclassification of protocol. Second one is whether serial communication or parallel communication. So when we have the serial communication and when we have the parallel, suppose I already told parallel in processor to memory communication, or whenever the processor is communicating with any of the component, it will communicate through parallel only. Okay, we cannot transfer the data serially. Every data is done parallel. Even it's a 32-bit data or 128-bit data or 256-bit data. Nowadays, every memory storage we are using 256 bits only, right? So entire whatever the size, all the data will be transmitted parallelly. Okay. So in this we have different types of protocols. Coming to the parallel communication, parallel protocols. AMBA protocols, whatever we are going to discuss, APB, AHB, AXI, all these things comes under parallel communication. But serial means USB, UART, PCIe, one of the high speed and within chip. USB means outside the chip. UART is also outside the chip, but low speed serial communication. Like that, you need to divide. Okay. All serial communication, PCIe, USB, UART, UART, all these things comes under serial. I2C, SPI also, but within a chip communication. Okay. Parallel means there will be n number of lines. If there are n number of bits, n number of lines will be connected. Serial means single line. Within a single line, one by one bit will be communicated, transferred. And next, coming to the asynchronous or synchronous communication. We have both. Nowadays, all the protocols are synchronous only, like AMBA protocols or USB, PCIe, everything serial, synchronous. That means it has same clock, works under same clock. But asynchronous means it doesn't have common clock. Transmitter to receiver doesn't have common clock. Then you may get the doubt, then without clock, how we can do the synchronization between sender and receiver. Means if you observe here, how it is showing start bits here near 0, start bits, and here also stop bits. Okay. Through the start bit and stop bit, we make the synchronization between sender and receiver. Once the stop is off, it cannot it cannot receive the data. Once the start is off, it cannot pass the data or transmit the data. And also errors, we will check the error, parity error. This is one of the in which protocol we use, in the sense UART protocol. UART protocol is a asynchronous protocol, and remaining all are synchronous only. I2C, APB, AHB, AXI, all these all comes under synchronous protocols. Okay, tomorrow we are going to discuss UART protocol, so you will get understand. And also you may get the doubt, so without, don't we use any clock between the transmitter to receiver? Okay, even start bits and stop bits are there, but start and stop bits will indicate that when to send the data and when to stop the data, right? But it doesn't generate the clock between transmitter to receiver, and it doesn't generate the frequency between transmitter to receiver. Of course, both are not working in synchronous, but at least the transmitter side and receiver side must have the frequency, right? Then only you can understand at what frequency the transmitter is sending the data and what frequency the receiver is receiving the data, right? So for that purpose, in UART protocol, we have a baud rate generator. Baud rate generator, in the sense it replaces the clock. It doesn't replace the clock. Actually, clock replaces the baud rate generator. Baud rate generator not replace the clock. Okay, baud rate generator is one of the oldest version. It's a it's a starting what we call concept. Okay, for frequency calculation between the transmitter and receiver, and how much data we are transmitting per second or at baud rate. Okay, we just classify that. Okay, so tomorrow we are going to discuss about the baud rate generator also. That means how many number of bits we can transfer per second. Okay, and there are a lot of limitations with the baud rate generator because the transmitter side and receiver side both will not work at a proper synchronization, and also it is very difficult to connect both the signals, right? So whenever there are a frequency mismatch, lot of data loss will be there. So here clock is replaced with a baud rate. Next, from I to C, SPI, even in APB, AHB, AXI, all protocols have the synchronous communication using clock. Okay. Any doubts still here?
Um, Ma'am, I have a doubt. Uh, PCIe is for communication inside the chip, ma'am.
Yes, inside the chip.
Okay.
Have you seen the PCI slots in motherboard? I think you already seen motherboard. Actually, if you see motherboard, there will have the bridges. North bridge IO, south bridge IO will be there. North bridge IO and south bridge IO, why do we use in the sense of same system on chip design? Suppose here there is a S4C. Okay, the processors, memories, wherever high speed data is there, these all are one side, and the remaining low speed devices all are one side. Okay, so from high speed to low speed or low speed to high speed, if you want to communicate like that, NBIO and SBIO will be used. North side north bridge IO, SBI south side south bridge IO we use to connect all the IO peripherals. Okay, so to communicate with these type of bridges, we use a PCIe slots. Okay, because a huge data is going to transfer, right, between subsystems to subsystems. So that's why we use PCIe. Of course, it's a serial communication, but very high speed communication. See here, north bridge, and here it's a south bridge. And if you see here, these white color or PCI slots, this one is a oldest motherboard. Nowadays we are not using these motherboard is nothing but there will be some PCB board. On that we will connect all the components. If any component is damaged, we can just replace with the another component. But nowadays everything is a automatic, like system on chip design. If any component is collapsed, we cannot change, right? It's very difficult to change that component again and again. And also if you see olden days, if you want to use a graphic processor, we need to buy separately. If you are using for any video purpose or any gaming purpose, or if you have Photoshop it like that, only those members will use the graphic processor which we buy separately. But nowadays in system on chip, everything graphic processors are integrated in a same SoC. Okay, because we are getting monolithic multi chiplet, everything the graphic cards are integrated in a SoC. But if you see here north bridge and south bridge IO, that means processor related, memory related, everything will be communicated, and this side data will be communicated to here using these bridges. Okay, and here it's a processor, and these we call as a PCIe slots, which used to transfer the high level data between all subsystems. See, these all are PCI 1, PCI 16, PCI. So these slots are used in the motherboards. Okay. If you see here, processor and how the wires also will be there. PCIe wires. I told lanes, right? We will communicate through lanes like this. These are not parallel communication. These are lanes. All are serial communication, but multiple data will connect in a lanes. One lane will transmit 64-bit data. One lane will transmit 128-bit data, like that. All 128-bit data will be transferred serially, but like that, 4 128-bit data will be transferred in a single lane. I think you got the point now. Okay.
Yes, ma'am.
So these wires will connect in these slots like this. Before I shown, right, those slots. Next, so this is what synchronous and asynchronous. And coming to the duplex, simplex and half duplex and full duplex transmission mode. What is meant by simplex? Do you have idea? Not
We
only
can
in terms
transmit
of
and receiving through single channel.
through single channel, both transmission and receiving.
We can
Both
transmit
can
and
be done.
receiving the data.
Okay. What is meant by simplex? What is meant by half duplex and full duplex?
Simplex only one direction communication. Only duplex means two-way we can do communication.
Okay. What are the applications like examples? What are the applications?
Walkie-talkie, a simplex example for simplex load.
Walkie-talkie. Okay. Next. Walkie-talkie simplex. Huh? Walkie-talkie is not simplex.
Radio is simplex.
Yeah, tell. So simplex in the sense, transmitter, receiver, we can transmit the data only in a single direction. Transmitter
Keyboard to
can
computer.
transmit the what? Keyboard
to computer.
Okay, from keyboard we don't get the data, right? Okay, keyboard to computer. Any other?
TV.
Keyboard to computer. Computer will send the data to keyboard, right? Only if keyboard sent to the computer, then how keyboard will understand whether it type or not? Keyboard keyboard will not get any data na, from computer. It just only type the data na.
Television.
Television also giving the output. We can control with the remote. Okay, television. Any other? Radio. Radio also same, right? Radio will give the output. We cannot control the radio, but television we can control the data. Is it correct? Radio. What about your keyboard? Is it correct? Keyboard? half duplex, not simplex. Both directions cannot be simultaneously.
Okay.
Okay. Next, half duplex transmitter to receiver. We can transmit the data both the directions, but cannot be at a time. So you said the keyboard now or walkie-talkie. So we can talk with the like it's like a mobile, but if both persons talk at a time, we will get the crosstalk noise will be getting, and even we can't hear what they are talking second person. Okay, so these two will be the half duplex communication. And coming to the full duplex, both can be done at a time simultaneously. Both a bidirectional transmission and receiving both are bidirectional and can receive at a time simultaneously. It is possible. Okay. Next, in terms of protocol, we need to discuss, right? In terms of protocol. So what protocol comes under simplex, half duplex, and full duplex? Simplex, no protocols. Half duplex, most of the protocols are half duplex only. UART, I2C, SPI, APB, AHB, all these things comes under this, because we can transmit and receive, but not at the same time. UART also, we can transmit and receive. Even APB also, we can transmit and receive the data, but simultaneously we cannot do that. Okay. And AXI comes under full duplex. AXI comes under full duplex. We can transmit and receive the data parallelly because we have the channels, most advanced protocol AXI. We will have the 5 different channels. Through the channels, we will transmit the data and also receive the data. That means write the data, read the data. Everything is possible. Okay. So that is what the difference between duplex, full duplex, and half duplex.
Ma'am, one thing, SPI is full duplex, right? Not half duplex. Once to my knowledge, it's not a half duplex.
Okay,
Saying it,
I2C is a half duplex, huh?
yeah, I'm not sure about I2C, but I know SPI is a full duplex because once the clock is generated, you can send and receive data also at the same time. So
Okay,
that's why.
using Mosley and
Yeah, MISO.
MISO signals. Okay, okay. Both can be done at a time, huh?
Yeah.
Okay, okay. I didn't work on SPI, but I know
Yeah.
I2C.
Yeah. So yeah, I just wanted to check. Yeah. That I'm sure. So that's why you said it is half duplex. So
Okay.
yeah.
Okay, fine. And here is the difference classification between UART I2C and APB, AHB, AXI. So I think you already got clarity where we use APB and where we use AXI and how high speed data will be converted into the low speed. Okay. So by tomorrow, everyone get the clarity between I2C, UART, I2C, SPI, and USB, UART, USB PCIe, APB, AHB, AXI. Compare these all, okay, and get understand which one high speed, which one low speed, which is a simplex, half duplex, full duplex, and which are parallel communication, and which are serial communication, and which are synchronous, asynchronous, and which are intra. Everything write a table. Okay, so you will get your doubts clarified, and whenever you want to refer in future, it will be easy. So all protocols try to make one classification and share to me. Okay, is it clear today's session? Any doubts?
Yeah, one thing like intra-connect I want to ask. So
Okay.
on the motherboard, where it stand like I2C or like how you shown PCI?
These are not PCI is a subsystem to subsystem. Suppose But these are not subsystem to subsystem, just within a IP to IP, and even in a functional blocks within IP also.
Okay.
Okay. Within a IP, we'll have a lot of functional blocks, right? Suppose within a IP here, SDRAM DDR4 is there. Here, this to this, we use serial communication, but we need to check those must be low speed only. Maybe for memory, it will not applicable. Here, low speed devices are there, display, PMU. So internal functional blocks, we use I2C and SPI.
Okay. We can see, right, in motherboard it will not show, right, anywhere.
In motherboard, it will not show.
Yeah.
See here, sensors, RTC, memory chips in embedded systems, like that we use I2C.
Okay, so it's on chip, but internally
Internally,
with two
serial
IPs,
communication. Yes, with
or
small.
inside the IP, two blocks.
Suppose sensors, how we will connect? Suppose FPGA board is there. For the FPGA is a functionality, right? To the functionality, we will just connect a external small component called sensor. So in that case, we use I2C.
Okay.
Okay. Others, any
Yeah.
other doubts? So tomorrow we are going to start with the UART, and next week I2C, like that. Each protocol two sessions, mostly 2 or 3 sessions. Okay, that is what I2C, APB, AHB, AXI. Everyone understand the application wise also. Okay, suppose the UART mostly internal device to external device. I2C, where we use I2C, mostly we use serial communication for temperature sensors or accelerators or humidity sensors. So whenever you are connecting some embedded system sensors to the main computer, or some flash memory configurations, we use I2C. Or even sometimes we connect the clocks, right, in S4C. Real-time clocks we connect, which are embedded related, to keep track the embedded devices. We use RTC, real-time clocks. There also we use I2C. And display modules, like here in S4C, I have shown here the display modules. So like if in display also, we will use different types, OLED or LCD displays, even IoT applications, from communication between microcontrollers or IoT devices also, we use I2C. In same way, SPI, both are similar, but few specification will be different, in terms of, suppose in I2C we use SDL, SCL clocks, and in SPI we use MOSI signals. I don't know SPI signals, like that. The feature wise, I mean functionality wise, I don't know the diagrams. Okay. Applications wise, we use in flash memories, communication purpose, display interfaces, high speed sensors, mostly these. But SPI is compared to I2C, it works at a very high speed. SPI. Okay, clear everyone? And also mostly in FPGAs also we use SPI to connect analog to digital converters, digital to analog converters also we use SPI.
Ma'am, these protocols are already standardized, right?
Standardized, yes.
Yes, means like how it will be changes when we work with the application level.
Application level in the sense, suppose this is application. Suppose if you consider it's a system on chip application, it's a very simple building block. But if you see here, suppose high speed side, this blue color AXI protocol. It's a standard. We cannot use any other protocol. Maybe internal industries, they may have their own protocol, but commonly used protocols are these. According to the application, these are all standardized. AXI means only for high speed interconnects. APB means only for low speed interconnects. Okay. PCIe means within a block to block serial communication. For high speed communication purpose, we use PCIe. Like that, I2C, USB for one chip, one device to another device, we use USB. Every laptop we have the USB, right? Like that. All these are standardized. Even network on chip protocols also same.
Okay, okay, ma'am.
SATA, CAN. Okay, so it takes some time to understand everything and to put all in one page, the classifications. Okay, you will get more clarity also, and write down all the things and share to me. Okay, I will also check. So that's it. Any other doubts?
Ma'am, the tool axis.
Yeah, I will share. We'll explain tomorrow or next week.
Ma'am, can you also share this PPT? It helps us to go through the materials.
Okay, I will share.
Ma'am, the recordings will be available, right?
Yes.
Okay.
I will share this PPT, recorded sessions and assignments. I will share access to your mail IDs. Okay. Okay, then thank you all. That's it for today. Everyone join for tomorrow's session at 10 a.m. Same timings.
Thank you.
Akash, do you
Okay,
have
ma'am.
any doubts?
Sorry?
Do you have any doubts?
No. Everything is.
Okay.
Yeah.
Sahana, Aditi, Sai, Krishna, Ranjit, Vinita. Any doubts?
No, ma'am.
No, nothing from my
No.
end.
No, ma'am.
Sai. Okay, fine. Okay, then. Thank you all.